Hey folks, welcome back to the wonderful but strange and Twilight Zone-like world of relativity. We are going to look at another consequence today. That consequence is something called time dilation, which we'll dive into in just a moment. But first, I just want to touch on what you can see on the screen right now. Remember, we've talked about the Michelson-Morley experiment, which determined that there was no such thing as ether, which led to something called the two assumptions of relativity. Number one, that there is no preferred reference frame for light. Kind of sort of meant you can't really tell who's moving. All we can tell is when people are moving relative to each other. And the other kind of crazy point was that the speed of light is always the same. It's always the lowercase value c, which is 3 times 10 to the 8 meters per second, even if the source or the observer is moving. And that's something that we're going to have to keep in mind for this video, because it is sort of the thing that leads to time dilation. So time dilation is going to be about sort of clocks not really keeping time the same way. I like to just, as a one sentence explanation of time dilation, this won't actually make sense yet, but it will in a moment. I like to think that the single moving clock runs slow. So let me walk you through what that means. I'm going to give you a couple of definitions here that we're actually not going to spend any time memorizing. So you can look at them. I don't even know if you need to write them down. Some people would say, hey, if you're looking at relativity and time dilation, you need to memorize these terms, but I have a different way for you to think about this that I think will be easier for you. There are a couple of ways you could measure how long an event takes. One of those ways is to measure how long, let's go with the trip to Vancouver. You're going to fly down to Vancouver. So one of the ways to do that is to record something called the proper time, which is the time measured with one clock. So in this analogy, if you're going to fly to Vancouver, maybe that's simply the pilot looks at their watch just as they're taking off from Penticton. They look at their single watch just as they land in Vancouver, and they can really quickly, based on those two times, figure out how long the trip took. That is called proper time, which is actually a misleading name, I think, because proper makes you maybe think that it's the correct way to measure time. But it's not. It's just one option of how you can measure how long an event takes. The other option, which is called the improper time, which is certainly a misleading name because improper makes you think that it's wrong, but it's not. It's simply another way to record how long an event takes, and this is weird. That would be the time measured with two synchronized clocks. So instead of the pilot measuring it just with their single clock, there would be two people, one of them, or an observer. Remember, we said an observer is like a line of people, all with synchronized clocks. So maybe there's two people or a whole line of people, and they have synchronized clocks, and one of them is standing on the runway in Penticton, and one of them is standing on the runway down in Vancouver. And at the moment that the plane takes off, the first person who's on the runway in Penticton makes a note of what time it is on their watch. Maybe it's 1:30. And the plane takes off and it leaves. They can't see it anymore, so they go home. That plane lands in Vancouver, and there is another observer sitting there whose clock is synchronized to the first person's clock, and they make a note of what time the plane touches down on the runway. Let's call it 2 o'clock, just to make life easy. So they make that note, they call up their friend on their phone, and they say, hey, the plane just touched down, it's 2 o'clock, what time did it take off? Well, the plane took off at 1:30. Oh, okay, the trip took 30 minutes, right? That would be a weird roundabout way to record how long it takes to fly down to Vancouver, but it works, right? So the pilot can time it with their single clock, they're in the plane, or a couple of people, one in Penticton, one in Vancouver, could simply have synchronized clocks and make note of what time the plane takes off and what time the plane touches down. So I have that picture here where we've got this airplane flying through the air. That is a stopwatch, by the way. I've had students before think they're turtles, right? Turtles without back legs or something. I don't know. It's weird. But we've got the pilot with their single clock. We'd call that proper time. That doesn't mean correct, because there's just different ways to measure time. Remember, this whole relativity discussion says there is no preferred reference frame when you're taking measurements. That says anybody's point of view is equally good. So the pilot's point of view, measuring with one clock, is just a different way of measuring than these two people on the ground. One person in Penticton, one person in Vancouver. They've got synchronized clocks, improper time, crappy name, right? It really is. Let's just call a spade a spade. So again, I don't like those names. It sounds like one of them is correct, one of them is incorrect. So I'm going to offer you guys in a moment a different way to think about this. But it turns out that if that airplane can travel really fast, or the ground can travel really fast compared to the airplane, we can't really tell, right? But let's just say the plane moves to make life easy. Those clocks, the amount of time they record, might not actually be the same. You're like, what? I thought we said the trip took 30 minutes. Well, yeah, that was 30 minutes according to the people on the ground, right? They saw the plane take off at 1:30 and land at 2. But the pilot might not agree about that sort of 30-minute trip. So let me walk you through why that has to be the case. So this is only a thought experiment. This is what Einstein sat down and he just thought about stuff, right? He had no way of proving any of this because they didn't have airplanes. We still don't have airplanes that can go fast or close to the speed of light fast. But we don't have things like photon clocks either. But let's pretend we do. So a photon clock, we're going to say what the photon clock is. And again, theoretical, just a thought experiment, but work with me here. A photon clock is a little particle of light, right? We've talked about light being a wave. Well, it turns out it's actually a particle too, if you want it to be. It's kind of crazy. So this little green circle is going to be a photon, a little particle of light. And we're going to put it in a clear tube, and these blue rectangles are mirrors. So if you could, and you can't do this, right? Again, just a thought experiment. But if you could trap that photon inside of that tube with reflective mirrors, top and bottom, then that photon would travel up, bounce off the mirror, travel back down, bounce off the mirror. It would sit here and it would just go up and down at the speed of light. And if you could sort of see that, like in slow motion, again, you can't, but don't sweat the details, right? Thought experiment, theoretical. If you could sort of sit there and watch the thing go up and down, or listen to it, tick, tock, tick, tock, tick, tock, you could use this simple equation, D equals V times T, and you could say, okay, every time it ticks and talks, it's traveled, let's make it a nice number. Let's say the photon clock is like 1 meter, right? 1 meter tall. You could say, okay, it ticked and it talked this many times, so it would be that many meters. 30,000 times, that means it traveled 30,000 meters. So if you sat there as the pilot and you just listened during your flight, because you're on autopilot anyways, right? You got nothing else to do. You could actually measure the distance the little photon travels. And you know that the photon travels the speed of light because it is light. It's a particle of light. And if you know D and you know V, you can simply solve for T, right? Weird. And you're like, why would you use a photon clock? Why wouldn't you just use like your wristwatch, right? Or your cell phone? Well, Einstein didn't have, cell phones. They probably had wristwatches. But again, don't sweat it. It works. It's weird, but it works. So the pilot is going to record how long the trip takes with this cool photon clock, right? They're a physicist. Curse of the physicist moment. They want to time something in a different way. And it would work. So the pilot, as they're traveling above the ground, sees that little photon just bouncing up and down 1 meter at a time, right? 1 meter up, 1 meter down, 1 meter up, 1 meter down. So the pilot sees the photon travel a short distance, just from the bottom of the clock to the top, and back down to the bottom, and back up to the top. It's just sitting there, the little photon, up and down, because that pilot is not moving relative to the clock. So they just see the little photon bounce up and down in a straight line. Now, here's where things get interesting. Here's your observer. Remember, observer means a whole bunch of people with synchronized clocks. There's a bit of an issue here. If they're looking at the photon clock, and we imagine that the airplane is moving compared to them, or they could be moving compared to the airplane, it actually doesn't matter. What they would see is they would see the photon start maybe here at the bottom, but as the photon is traveling upwards, the airplane is also moving sideways. So these people down on the ground, if they were watching the same clock, an observer, the people on the ground, would see the photon travel a longer distance, right? It would actually be traveling sideways, this direction, and up at the same time. So they'd actually see it travel like the hypotenuse of a right angle triangle. They'd see it travel a larger diagonal distance because the plane was moving relative to them. So let's see if we can sort of figure out what the issue is. They each measure a different distance, right? So the pilot says, no, it's 1 meter up, 1 meter down, 1 meter up, 1 meter down. And the people on the ground, so there's the pilots, 1 meter up, 1 meter down. The people on the ground go, no, it was way longer than a meter. Look at how far that photon traveled. To get from the bottom of the tube to the top of the tube, maybe it traveled like 5 meters, right? Who knows? If the plane was going really fast, maybe it traveled like 10 meters. Who knows? But it's going to travel this longer diagonal distance. They just see it travel a different way in their reference frame. But both parties are correct. Both parties also are correct when they make this statement. They disagree about the distance the photon is traveling, but they do agree that since it's a photon, it is simply traveling at the speed of light. So remember that the people on the ground, you don't add any velocities when you're talking about light. It's simply 3 times 10 to the 8 meters per second. So here's where we end up with an issue, right? If you compare these 2 points of view, maybe I'll just ink this in here. This might be easier. Let's do the pilot point of view, or the pilot's reference frame. And then we've got the ground reference frame, the observer. I'll just call it ground, the ground point of view. So each of them says, yeah, we can use that photon clock to calculate time using the simple d equals v times t that I mentioned earlier. The issue is, again, that they disagree on the distance. Remember, the pilot sees the photon just travel like 1 meter up, 1 meter down. The pilot sees that photon travel a short distance, but the people on the ground, they're going to see it travel a long distance, that diagonal distance. They both agree on the velocity. The velocity is simply 3 times 10 to the 8. It's the same value, right? It's locked in. The speed of light is always the speed of light. So if they agree on the velocity, but they disagree on the distance, they're going to have to disagree on the time, right? It's the math proves it. You can't have agreement on time if you disagree about the d in this equation. So a short distance for the pilot means they're going to measure a short time, and a longer distance traveled by that photon means it's going to take longer to do that. They're going to measure a longer time. Now, you might be looking at that going, okay, I can kind of wrap my head around that, but that's a photon clock, right? What happens if you get a wristwatch? And it turns out that if this is the case for one type of clock, it has to be the case for all clocks. If time is going to change with a specialized theoretical photon clock, then it has to be the same. You're going to have the same disagreement with wristwatches, with cell phone clocks, with any kind of clock. So let's see, what do I have here? D equals V times T. Yeah, so I've got something very similar in the notes here. So the result, here's where hopefully that'll make sense. The single moving clock runs slow. So the people on the ground look up at that pilot and say, oh, you have a single clock, right? And it's moving compared to us, because we would think that the airplane is moving and the ground is stationary. And those people would look and they would say, ah, your clock's running slow. So if I scroll back to this picture, that trip from, there we go. The single moving clock runs slow, and then the people who stay on the ground, the multiple clocks, the multiple people that measure, they're going to measure a larger time. Okay, sorry. Just fielded a phone call and I totally lost track, and I don't really know where I was, let's be honest. I have very little memory. We've talked about how the clocks have to be different. We've talked about how the pilot with their single moving clock is going to run slow. So if I go back to that analogy where the people on the ground had said, what did we say, 30 minutes or something like that? So they're going to measure a longer time. And the clock, or the time measured with one clock, is going to be smaller. It has to be, because they see the photon travel the smaller distance. The people on the ground see the photon travel the longer distance. Just for example, if we go with that 30 minutes that I had mentioned sort of at the start of the video, just making these numbers up, the people on the ground, let's say they measure 30 minutes. They might then talk to the pilot and say, hey, that was a nice quick trip, eh? 30 minutes? And the pilot goes, what? What do you mean 30 minutes? And the people on the ground are like, well, you took off at 1:30 and you landed at 2. 30 minutes. And the pilot goes, no. I didn't take 30 minutes. My trip took 20 minutes. Their clock actually elapsed by 20 minutes. That means that for people who were on the ground, 30 minutes actually went by. And for the pilot, who was in their airplane flying, 20 minutes went by, right? Actually 20 minutes. It's not like, oh, you thought it was 20 minutes. 20 minutes elapsed according to the pilot's watch, and 30 minutes elapsed according to the watches of the people who stayed on the ground. That means that once the airplane lands and it's not moving anymore, that means that the pilot's watch might show, what did we say, 1:30 and 2 o'clock? So the pilot would go, no, look at my watch. It only says 1:50, right? It only shows that 20 minutes has elapsed. And the people on the ground are like, well, our watches show that 30 minutes went by. Our watches show 2 o'clock. And as soon as the pilot stops moving, because we can tell that, right, when people aren't moving relative to each other. Once the pilot stops moving, then the clocks fall back in sync. Everybody's clocks, the pilot's clock would be keeping time at the same rate as the people on the ground, but it would still be that 10 minutes behind, right? That pilot actually lost 10 minutes, or the people on the ground actually gained 10 minutes. But as soon as we stop moving, then the clocks all fall back in sync. It's kind of a crazy concept. Let me walk you through a more aggressive example. Again, just thought experiments, right? What if you put somebody on an airplane, and the faster the airplane is traveling, the more aggressive this time change will be. And it goes back to that gamma calculation. Remember, we talked about beta and gamma, and we said gamma was this weirdness factor. That gamma value tells you how different the clocks will be. So let's say that the airplane is traveling at like 90, what do we say, 90-ish% the speed of light, I think gave us a gamma value of around 2. So that means the clocks would be different by a factor of 2. So here's what's kind of crazy. What if we put somebody on an airplane? We're going to put Susie on an airplane. She's going to go fly around, and according to her watch, 1 year's worth of time elapses. So 1 year goes by. If she's traveling at some speed that gives us a gamma value of 2, it's probably around 90% the speed of light. That means for you and I, who stayed on the ground, 2 years worth of time would elapse. Now what's crazy is that this is not like some illusion, right? Where it actually is like somehow 1.5 years, like you split the difference or something. Susie gets on that airplane. She is 16 years old. And when she returns, 1 year has gone by on her clock. She goes to bed 365 times and wakes up 365 times. She sees the sunset 365 times. She sees the sunrise 365 times. She comes back and she's 17 years old. You stayed on the ground. When Susie took off, you were 16 years old, but you had 2 years worth of sunrises and sunsets. You got 2 years worth of stuff done. When she returns, you're 18 years old. You don't appear to be 18, you're actually 18. She doesn't appear to be 17, she is actually 17. Let's go even a step further. Here's where it gets really weird. What if we put Susie on the airplane and we make her go so fast, or she's got this like wicked airplane, she can go like 99.9% the speed of light. And what if we get a gamma value of 20? So let's think about that. What if gamma was equal to 20? What if the clocks were off by a factor of 20? That means Susie gets on the airplane. 1 year goes by according to her watch. She ages according to time in her reference frame. So she gets on the airplane at 16 years old. She has 365 days of time on her airplane. She comes back and she's 17 years old. She's actually 17. She looks 17. She is biologically 17. She got only 1 year's worth of stuff done. 365 days. She ate breakfast 365 times. Here on Earth, right, on the ground, you and I stuck around. We'll go with your age, though. 20 years has elapsed because that gamma value is 20. So your clocks are 20 times faster than hers, or hers is 20 times slower than yours, however you want to look at it. That means when she comes back after what she thinks is 1 year, because it was 1 year according to her reference frame, she comes back and you guys are 20 years older. You're like my age. You're 36. You are actually 36, right? You look 36. You have kids. You have a career. You maybe own a home because you are 36, right? Like 20 years worth of stuff has occurred. Whereas for her, it's only 1 year worth of stuff has occurred. Now, I want you to keep in mind, sometimes people look at this and they're like, whoa, I want to be on the airplane then because it's like time slows down, you live longer. You don't actually live longer, right? If you're on the airplane, Susie only got 1 year's worth of stuff done. She left in grade 11, she's still in grade 12. She only got 1 year's worth of schooling done. In your reference frame, you got 20 years worth of stuff done. You've graduated, you've maybe gone to post-secondary, or you got a job. Again, you've got a career, maybe a family, or you're living in your parents' basement. No judgments. But really what's happened is she's just kind of living slower, and you guys are just living faster, right? Time is just elapsing at a different rate in your reference frames. So it's not like you're living longer, right, if you're up on the airplane. The only I guess if you call this an advantage, I'm saying this in air quotes, is if you're in that airplane, 1 year goes by, you come back to Earth and 20 years has elapsed on Earth. The only kind of cool thing is that it would only take 1 year to see what 20 years worth of like technological innovation looks like. So that might be kind of cool, right? Like she leaves, 1 year goes by, she comes back to Earth, and we've got like totally autonomous self-driving cars. That'd be pretty neat to see, right? And like she skipped the whole development and all the car crashes that came with the early ones. But again, she's just living slower and you guys are living faster. This also means, here's a really weird thought experiment. This video is going to get kind of long, but there's so much cool stuff that I would love for us to talk about in the next Zoom meeting. Think about if you put your parents on the airplane. Right? You could put your parents on the airplane and fly them around for 1 or 2 years, and if that plane were going really fast and gamma were really big, lots of time would go by here on Earth. You could actually have your parents come back after their airplane trip and be younger than you. Right? Because maybe they only aged 2 years, but you aged 40 years. And they would actually be younger, right? Physically, biologically, they are actually younger because they only got 2 years worth of stuff done. They were 45 when they hopped on the plane and they got off at 47. And 40 years went by for you. You're 56 years old, right? You're actually 56. So that whole thing, my parents tell me that, hey, When I was a baby, they changed my diapers, but I'm going to pay them back because when they're old, I'm going to be changing their diapers. My parents are in their 60s, so they like to joke about that. Well, if I could stick them on the airplane and fly them around really fast and have them come back younger than me, they'd still be changing my diapers because I would hit that diaper age before they do. So maybe that'll happen. Maybe we'll develop really fast-moving airplanes by the time that happens. So let me scroll ahead again. You've probably got some bargaining, some questions you want to ask. So like write those questions down. Let's chat about it in Zoom because for some of you, the conversation is going to be awesome. I really hope we can have this conversation. Let me scroll ahead and show you what the math looks like. Crazy concept, but easy math. Let's try. We're going to skip all of this, blah, 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 because there's a better way to think about it. Okay, let's think about this. Pilot drinks a cup of coffee while flying at a speed of 2.6 times 10 to the 8 meters per second. That is like almost speed of light fast. We do not have airplanes that can go that fast yet. Theoretical question. The pilot says it takes 7 minutes on the nose to drink the cup of coffee. What do observers on the ground say? Now, if you look at your formula sheet, you're going to see some equation on there with like T's and T naughts and gamma. And I don't even remember the equation, to be perfectly honest. We're not going to use the formula on the formula sheet, whatever it looks like. I should probably show it, but you could go find it. We're going to remember this. This is the equation for time dilation. The time recorded by 2 clocks is always bigger than the time recorded by a single clock. That's the equation I want you to use. Very, very easy. The 2 clock time is bigger than the 1 clock time. So if we look at this question, here's what we have to ask ourselves. They've given us 7 minutes here. How many clocks measured that? And you can read the question, you can say, oh, okay, well that was the pilot. The pilot only has 1 clock. And it's not like, oh, the pilot's wearing like a watch and they have a cell phone and maybe another watch on their other hand because they're all blinged out. No. The pilot measures with a single clock. So they're giving us the single clock time, and then they say, what do observers on the ground say? Well, observers, multiple people, they're each going to have a synchronized clock, right? So what we're looking for in this case is the 2 clock time. And that equation says, okay, the 2 clock time that we're looking for has to be bigger than the 1 clock time that we were given. So how do we make 7 minutes bigger? And the answer is, we simply use gamma, right? That's all you need to do for these questions is figure out beta, use that to get your gamma value, and then if you want to make a time bigger, you multiply by gamma. If your goal is to make a time smaller, if you're trying to get the 1 clock time, then you would simply divide by gamma. So it's actually a pretty slick drill. Let me fire up my calculator here and we'll give it a try. All right, so the first thing we have to calculate is beta. Remember, beta is the velocity that you're traveling, 2.6 times 10 to the 8, divided by the speed of light, 3 times 10 to the 8. So we get a beta value here of 0.867. Maybe I should show that calculation. It's the first one we're doing today. So beta is V over C. That equation is on your formula sheet. You'll have it memorized in no time. 2.6 times 10 to the 8 divided by 3 times 10 to the 8. We get this beta value of 0.867. That means this airplane is traveling at 86.7% the speed of light. That's getting pretty close. We're then going to take that value and turn it into gamma. So remember, gamma was 1 divided by the square root of 1 minus beta squared. And again, you need to be able to do this calculation. I'm snapping my fingers like that fast, over and over and over again. So 1 divided by the square root. I'm going to use the answer button just so I don't end up with rounding issues. 1 minus beta squared. Close the bracket. There you go, 2.004. I'm going to take sort of some extra decimal places again just so I don't end up with rounding issues. 2.004. That's a key number here. That's the number we're going to use to make the 7 minutes bigger. Because remember, that 2 clock time is bigger than the 1 clock time. So the time that we're solving for in the end, I don't really care if it actually should have the little zero. It's called T naught when you put the little zero there. I don't care if it's technically supposed to be T naught or just T, proper time or improper time. We don't worry about that. We're just going to call it T for time. The time recorded by the observers, we know the 2 clock time is bigger than the 1 clock time. So we're simply going to take our 7 minutes and we're going to multiply by gamma. 2.004. And I think, well, that should give us just 14.0 times 7. Yeah, there you go, 14.0 minutes. So here's the sort of crazy part at the end. How long did it take to drink that cup of coffee? Did it take 7 minutes or did it take 14 minutes? And I like to joke that the answer is yes. There's usually an awkward pause, just like there was there, and students are like, well, Heinrich, what do you mean by that? Yes. So did it take 7 minutes or 14 minutes? Yes. Did it take like some time in between? No, not some time in between. It actually took 7 minutes and or 14 minutes. It really depends on where you're measuring from, right? It's crazy. But both answers are correct. It just depends on your point of view. So I'm going to open up the homework that goes with today and try a question out with you and then turn you loose. I think there's like 4 questions for you to try or something. Let me do one of the 4 with you. We'll get 25% of it done, and then you can finish up the other 3. All right. So your practice that goes with this lesson is just the first 4 questions on this worksheet, Relativity Worksheet 1. So I would like you to try number 1. I will let you play around with that. I would like you to try number 2. Let you play around with that. I want to do 3 with you because I want to show you something kind of cool. Here, I guess in number 2 it says a very long train full of people travels past a farmer working in a field. Then it says in number 3, a second train passes the same farm. So hey, I grew up in Armstrong, right? We got some farming examples here. A train is going to go past a farmer, and it's traveling at 0.720 c. This is actually a weird way to state a velocity. And maybe I shouldn't say weird. It's actually a nice way to be given a velocity, and let me show you why. We're used to velocities in meters per second, but in relativity sort of calculations, sometimes velocity could be given as a beta value with just like a c attached to it. And what that's telling you is it's telling you what percentage of the speed of light the object is going already. If you needed to convert this value into meters per second, you would do exactly what this number tells you to do. You would simply go, okay, 0.720 times c, done. 0.720 times c is the speed of light, 3 times 10 to the 8. Okay, so this train is going 2.16 times 10 to the 8 meters per second. It actually turns out that this velocity given as a beta c value is actually nice for us in terms of our calculations, because watch what we're going to do here. In number 3, it says, so this train is going past the farm at 72% the speed of light. It's traveling really quick. The people on board, notice that it takes 3.5 minutes for the farmer's son to milk a cow. How many clocks measured that? The people. People is plural. So that 3.5 minutes is actually a 2 clock time. Sorry, that's supposed to be a clock. It looks terrible. We want to know the end goal here. How long does the son, so the farmer's son, how long does he say it takes for him to milk the cow? Well, he's a single person. He's only got 1 clock. So we want the 1 clock time. And what do we know about the 1 clock time? Well, we know that the 1 clock time is smaller than the 2 clock time. Right? 2 clocks always measure more time than 1 clock. The observers measure more time than the single clock, the single person. It actually, I should throw this in there, it doesn't matter who's moving, because we can actually never tell who's moving. So I don't want you to go, oh, the people on the train, they have to measure the shorter time. Nah, it doesn't matter about the train moving, right? We could just as easily say it's the ground moving past the train. So when we're figuring out this clock thing, don't think about who's moving. Think about where do you have multiple clocks and where do you have a single clock. That's all that matters, right? Is the plural, the people, versus the singular clock. So we're looking for that single clock time. It's smaller. So we need to somehow get this 3.5 minutes into a smaller number. It's going to take less time for that single clock. Or less time will be measured by the single clock. So how do we do that? Well, first we find beta. Beta is equal to V over C. And check this out. If you're given a beta C value, this is really slick. 0.720 times C divided by C. Awkward pause. People are looking at that, hopefully going, oh, nice. The C's just cancel out. You don't even have to show that calculation, right? Let's get smart. There's beta right there. So it's kind of cool to be given a velocity in that form because it saves us from having to do the beta calculation. Now we can calculate gamma, which is 1 over the square root of 1 minus beta squared. Throw that in my calculator. Again, this needs to be automatic. There it is. I'm going to take 3 decimal places, but use the answer button even on my calculator. 1.441. So that number tells me, that's the weirdness factor, that tells me that the sun's clock is going to be 1.441 times shorter, smaller, than that 3.5 minutes measured by the people on the train. So if I want to make the 3.5 minutes smaller, my only option is to divide by that gamma value. Pretty sweet math, right? It's like you multiply by gamma or you divide by gamma. That's it. So grab the calculator. 3.5 divided by that gamma, that weirdness factor, gives us 2.43 minutes. Final answer. How long did it take? Did it take 3.5 minutes to milk the cow, or did it take 2.43 minutes? Yeah, sure. Yes. It actually took both amounts of time. It depends on where you measured from. Boom. Mind blown. Crazy. So there's number 3 done. Try out number 1, try out number 2, try out number 4. Check those answers. And please join me next week or this week. I'm making this video on the weekend. Join me this week in one of our Zoom meetings. I would love to bargain with you and hear some of your crazy questions, because I'm sure your brain is just whirring along and the gears are turning. Have fun with this, folks, and we will chat very soon.